Hi, and welcome to this session on delivering life-changing medicines at AstraZeneca with data and AI. My name is Chris Scott, and I'm a Global Solutions Architect at AWS within the Healthcare and Life Sciences industry vertical. I'll be joined in this session by Anna Asperg, the VP for R&D IT at AstraZeneca. So, what are we going to cover in this session? Firstly, we're going to look at the process of delivering these life-changing medicines at AstraZeneca, where they were and the challenges they were looking to overcome. We're then going to take a look at the architecture and how AstraZeneca have combined both data and AI within their drug discovery platform on AWS. Anna's going to summarize the outcomes for AstraZeneca and, importantly, the key lessons learned from the journey they've been on. AstraZeneca are always looking to continually improve. We will take a look at what's next and finally wrap up the session. Life sciences organizations are moving towards digital transformation, looking at how they improve collaboration, make data-driven decisions, enable faster development of new therapeutics. But identifying the right cloud technology to reach these goals can be challenging. To help customers accelerate their transformation, this summer we announced AWS for Health, an offering of AWS services and AWS partner network solutions to help organizations increase their pace of innovation, unlock the potential of health data, and develop more streamlined approaches to therapeutic development. AWS for Health aligns multi-purpose built services and hundreds of AWS partner solutions across 5 critical solution areas in pharma, so customers can more easily identify the right cloud technology to accelerate their business transformation and reach their business initiatives faster. In this session, we focus in on research and discovery and how cloud technology has been used at AstraZeneca to accelerate the identification of potentially new changing medications. With that, I'm excited to pass over the mic to Anna Asperg, VP of R&D IT at AstraZeneca.
Thank you very much, Chris. I'm here and I'm pleased to represent AstraZeneca. AstraZeneca is a global biopharmaceutical company that's focused on discovery, development, and commercialization of prescription medicines. We are active in oncology, rare diseases, cardiovascular, renal, respiratory, immunology, and metabolism. We operate in over 100 countries, and its medicines are used by millions of patients worldwide. Today, I'm excited to tell you about data science and AI and how it's transforming R&D, help us to turn science into medicines more quickly, cost-effective, and with higher probability of success. I'm heading up R&D IT, and R&D IT's role is to be a critical partner to the world-class R&D organization at every single step of the journey that you see on the PowerPoint behind me. We partner with R&D so they can be focused on the complex path of getting medicines to patients. It starts with target discovery, where in average in industry, we run 10,000 parallel tracks of ideas, moving this chain through drug discovery, where we develop the candidate drug, preclinical testing, where safety is tested, and then moving into clinical trials, phase 1, 2, 3, where we engage with patients. And then, if it's successful, submission and delivery. And going from 10,000 in the beginning brings one medicine to the market in general in the industry. And it takes about 10 years to get one medicine to patients on average. Our role as R&D IT is to use technology to transform the speed and the quality of every single step of the journey, and having an impact on the delivery of medicines to patients. We feel humbled to work with technology in such an important area and have ability to impact people's lives. All of us have some personal story. We know someone who got cancer. We know someone who has a chronic disease. And it's incredibly proud for us to be able to touch the loved ones or even ourselves. My story, what motivates me to come to work every day. My father got cancer a couple of years back, and he didn't know how much time he had left. It could be very short, it could be a little bit longer. But thanks to medicines, he got actually a few years extra. And he could spend that time with the family, with me, my children, my brothers, everyone. He could travel and bring it closer. And I think it was incredibly important for us not to lose him so quickly, but actually get that extra time with him before it ends. And I feel so proud of what we do at work. And we really feel our mission. And I'm thinking about my dad. So why am I here talking about tech in a conference about pharma R&D? What is the connection? There are really two problems that we can tackle with technology. And those two problems are general for the entire pharma industry. One is, can you make a better decision earlier? Imagine if a technology really could help us to make the decision earlier. We start with 10,000 parallel ideas to get one medicine to patient normally. And if we with technology can make the insights to take decisions earlier with quality, we could with confidence take down the number of parallel tracks going on. The other one, imagine we could reduce the end-to-end time for getting the medicines to the patient. On average, it takes 10 years to get a new medicine through the whole journey and out to the patient. Imagine if we can contribute to the speed with technology, shave off days, weeks, months, and years. Imagine the impact of getting one new life-saving medicine faster to the one patient that need it. So this is what we were talking about today, the end-to-end process of R&D and how we build tech that make better decisions earlier with quality and how they can lower the number of projects we need to keep going in parallel. And we will also talk about how we reduce the time, how we automate steps, predict to cut iterations and shave days and weeks and months and get it quicker to the patient. But more important, it's not an isolated idea or a proof of concept we've done in one place. We have embedded AI through the whole process from discovery to delivery. And we've been on a change journey, and we believe that getting the wheel in motion, and it's important to have an impact to get it implemented end to end and not only in one step. So I'm going to share examples and step you through examples from every step of the journey. You will see examples from target discovery, drug discovery, all the way to safety. These are examples, of course, from AstraZeneca and applicable to the pharma industry, but I believe that they have a parallel use case in most industries. But first, as we wanted to go large, we wanted to go end to end, we had some tech challenges that we had to tackle, and I want to describe some of those we faced and the onset. So number one, data silos. We have more data than ever. And one of the problems we had is we needed to take care of the data. We need to make the data fair, findable, accessible, interoperable, and reusable. We had limited performance and capacity, and we needed the compute to handle the huge data set in real time that we're going to have. And we also started with limited use of AI ML. We had pockets of AI ML for many, many years, but we weren't using it systematically and we needed help to get there. So we partnered with AWS to address some of these challenges. AWS provided critical compute power to help us handle the enormous data sets and complex algorithms. They understand how we unite to support our R&D business and brought the right service to us. And you will hear from Chris later today and the architectural guidance that helped us to accomplish these incredible things. But let's start to look into some of the examples. How we use AI in research and development. One of the earliest stages, as mentioned before, it's discovering what disease target to go after. And here we have to handle an explosion of data. And I'm sure that many of you also have an explosion of data because that's how every problem we're all facing. But for us, it looked like we had a company-wide genomics initiative that in particular was challenging around data. We were aiming to analyze up to 2 million genome sequences by 2026, including from our clinical trials. And we have petabytes of genomics data, and we need multiple cutting-edge technologies to glean insights from it. To rapidly process the data at scale, we used Amazon Web Services to build fast, efficient, cloud-based solutions that could extract insights from genomics data. We can now run 110 billion statistical tests in under 30 hours, studying the effect of individual genes or diseases. We provided genetics input to more than 45 of our drug discovery projects and using those internal capabilities. Many of you probably know that building an amazing AI solution is only half of the battle. You also need people to trust it, use it, and see the value. And this has been a lot of our experience. So we have built sophisticated computational methods to predict what molecules can make next and how to make them. And traditionally, our chemists did design, make, test, analyze. You could call it trial and error, but sophisticated trial and error, to gather analyses over and over. The process could take years. Now they use AI to decide the best way to make the molecule in the shortest time. So we made our AI easy to use, and we not only built the solution, we also invested with a change journey and worked very closely to make the adoption. And now 70% of our projects are using this AI tool. And I would say the chemists are trusting it and they're working with us to improve it every day. So change management and user experience is so important when it comes to driving AI adoptions. Don't forget that. I'm sure that many of you see value in automating steps in how you do things in the workplace, process, or optimize workflows. No doubt the pandemic transformed the way of working for us all. During the pandemic, we accelerated efforts to digitize our workplace, including our R&D labs. We modernized hardware that our scientists have. As they walk into the lab, we wanted to have computers that connect to research instruments and were possible to also run experiments remotely. We put a lot of effort in optimizing the workflows. And for example, we really have intense data generating instruments, and we work to automate and harmonize data capture to accelerate decision making. This enabled faster, easier collaboration between our bench scientists and our data scientists that applied artificial intelligence and machine learning in the cloud to uncover new insights that previously required months in the lab. Don't we all rely more and more on imaging? How many of you unlock your phone with face recognition, for example? I do it so many times a day, I can't even count it. For us, imaging is very important. Imaging can give us insight. Image from biosamples can give us image on how disease behaves, which patient may be a right fit for our medicines. And when we get the samples, the old process was to blow up the image and have a pathologist manually annotate the picture to what to include and exclude in analysis. And with AI, we can do this differently. We use the machine learning algorithms to reduce the image analysis and give our pathologist time to focus on what's important, focus on the interpretation and findings rather than annotate, which is a part of the data collection. In another case, we implement an approach inspired from how self-driving cars understand their environment, and we trained AI system to score tumor cells and immune cells for biomarker called PD-L1, which has the potential to help immune-based treatment decision for bladder cancer. And we all have complex projects to plan and execute. And we want all to provide frictionless experience for our customers, no matter which industry we are in. For us, our most complex projects are probably the clinical trials that involve thousands of patients, that has a very complex process to step through, where we need to deliver medicines, we need to collect data from them. Advances in data science and AI are helping us to rethink how we design and deliver clinical trials, using data from previous trials. Also, once we come to the trial itself, one of the most exciting advances we have is the ability to collect data from a patient in their home on a daily or even continuously basis during the trial. And that data is as reliable as the one collected in the clinic. It helps really to improve the patient experience by making the participation more convenient. Such data can also add considerable value because it can tell us what's happening between the study visits in the clinic and give us advanced warning of important clinical events. Customer feedback is a critical tool for any industry, and pharma is no different. In fact, once our medicine is on the market, the job is not done. We have to track feedback continuously with safety events. By using NLP, natural language processes, we can do it better, faster, and with better accuracy. We enabled connected internal systems and analytics-ready data to help us gather and share information much more quickly across our clinical and regulatory teams, as well as with external health authorities. This sets us up for success. The application of AI, for example, detect and triage safety signals or data patterns. So hopefully you have a sense for how we are applying technology to transform R&D. All the way from target identification, through drug discovery, through preclinical, clinical trials and safety. And you can see how the examples, they are pharma unique, but there are many parallel user cases in the industry. Now I will hand over to Chris that will focus on our progress in augmented drug design, step number 2 on our process, which is all about determining what molecule to make and how to make them.
Thank you, Anna. Let's take a look at how AstraZeneca have used AWS to help solve these challenges and help accelerate the drug discovery process. Let's dive deep into the architecture. One of the technical challenges highlighted by Anna was the siloed data. This is a common problem many customers have, not just in life sciences. Unlocking this data can help many businesses generate much more insight from this valuable asset. To address this challenge, firstly, we're going to build out the core scientific data hub platform, centralizing the data on AWS, and then build out a common, consistent, scalable chemistry application gateway to provide application integration and scientist access. As we look through the architecture supporting the drug discovery process, we need to understand the core tenets which have guided the architecture design on AWS. Let's start with managed services. Like many customers, AstraZeneca decided to use managed services wherever possible. where AWS performs the undifferentiated heavy lifting, allowing AstraZeneca to focus on delivering business value. Secondly, was moving away from traditional monolithic application architectures and use microservices. This provides small independent services which can easily scale on demand, which shortens the development lifecycle to deliver value to the scientists sooner. Another tenet was to use open source software wherever possible. AWS is a proud supporter of open source projects, foundations, and partners. And finally, using infrastructure as code to create and maintain the platform build, allowing AstraZeneca reproducibility, version control, and consistency of environments. You will see these tenets throughout all the AWS architectures we take a look at. AstraZeneca made the decision to use Amazon Elastic Kubernetes Service as their managed container service, providing the scalability for the build-out of their microservices architecture. Aligned to the open source architecture tenet, Amazon EKS is fully compatible with the Kubernetes community tools and supports popular Kubernetes add-ons. If we start at the top, a combination of Jenkins and Argo CD is used to deliver full CI/CD capability for the microservices. The infrastructure stack is built out using Amazon Cloud Development Kit, as this allowed them to use the skills they already had in-house. The Amazon EKS cluster is provisioned across 3 availability zones with managed node groups to automate the provision and lifecycle of the nodes, with initial configuration of 12 M-series EC2 instances. Istio is used as a service mesh which provides application-level networking, making it easier for the services to talk with one another. It also provides end-to-end visibility and high availability for these services. This capability provides the foundation for the drug discovery platform to be built upon. First, let's look at breaking down the data silos and delivering a centralized data hub of chemistry data. AstraZeneca sources its data from many places to create the data hub. It is key we have a solid hybrid architecture. Firstly, we have their data centers. Like many large enterprises, there's still many applications running on premises containing very important data. Secondly, we have external data. AstraZeneca uses many third-party data sources to augment what they have internally. It's essential to bring this data into the central data hub. We also have the on-premise labs containing experiment instrument data, electronic lab notebook data, and file shares. And finally, we have contract research organizations or CROs. AstraZeneca partners with many CROs to deliver scientific outcomes. Sharing of the data is key between these organizations. Although not shown on this architecture diagram, the on-premise labs have WAN connectivity to the corporate data centers. Each data center has connectivity to AWS via 2 10 gigabit per second direct connect connections, both in the US and in Europe, to provide the required bandwidth and resiliency. Many of the on-premise chemistry databases are still running on commercial database engines. Like many other customers, AstraZeneca made the decision to break free from the commercial-grade databases and use open-source databases. Aurora PostgreSQL provides AstraZeneca with a fully managed capability, allowing them to focus on delivering scientific outcomes rather than standard DBMS maintenance tasks. Aurora PostgreSQL provides the throughput, scalability, and availability requirements for the data hub. Recently, AstraZeneca have made the migration to use the Graviton2 EC2 instances, custom built by AWS using the 64-bit Neoverse cores, providing an up to 20% performance improvement and an up to 35% price performance improvement for Aurora. The AWS Schema Conversion tool was used to perform a number of heterogeneous database migrations to PostgreSQL. The database migration service was used to migrate the initial load of data from the on-premise databases and continues to run a capture data change DMS task from on-premises data source to Aurora PostgreSQL target, as the on-premise systems are still being used. Using Amazon EKS as the platform for the microservices, the architecture diagram shows a small subset of the ETL microservices. Argo Workflow is used as an open source container native workflow engine for orchestrating the parallel jobs in Kubernetes. Istio provides a service mesh allowing the different services to talk one another. The various ETL microservices are used to ingest the data into Aurora PostgreSQL and S3. Amazon Athena queries can be run by the scientists to query the data in the S3 buckets directly. Discrete microservices have been built to provide RESTful API access into the chemistry data hub, acting as a gateway to all the chemistry data. Each microservice scales independently from one another depending on the load. This provides a common integration and authentication pattern for downstream chemistry applications and scientists to consume directly. Ingestion and access to data is key to unlocking the scientific data. Search is also an important tool in the scientist's toolbox to find new potential molecules. As primarily a technologist, I was intrigued as to how a molecule could be represented as something a computer could understand. Molecular fingerprints are a way of encoding the structure of a molecule. The most common type of fingerprint is a set of binary digits or bits that represent the presence or absence of a particular substructure in the molecule. Comparing fingerprints allows you to determine the similarity between two molecules or to find matches to a query substructure. In the example on the left-hand side of the slide, we can see a binary representation of the active molecule. On the right-hand side of the slide, we can see a representation of the stored molecules. Performing a similarity search across the stored molecules produces similar structured molecules, whereby, in this example, number 3 has the closest similarity. So back to our architecture. Now that we've understood about molecular fingerprints, how do we create them? How do we query them for substructure and similarity searches? The key to the solution is using Amazon OpenSearch service. First, let's focus on creating the molecular fingerprint. As data is inserted or updated into the Aurora Postgres database, a change data capture DMS task is capturing those changes. Amazon Kinesis data streams is configured as a target within DMS. A Lambda function consumes the Kinesis data stream and triggers an ETL microservice, which creates the required fingerprint and mole file to ingest it into OpenSearch, which is then indexed. The scientists can then call the API to perform similarity searches with Amazon OpenSearch and retrieve similar molecules in milliseconds. Traditionally, this may have been delivered using a relational database. However, using OpenSearch is a simplified process for AstraZeneca, providing rapid search capability and reduced support overhead. With over 1 billion molecules stored in OpenSearch, the architecture needs to be performant. The Amazon OpenSearch cluster is configured using 3 availability zones using the i3 EC2 instances as the data instances. The i3 EC2 instances are the next generation of storage optimizer instances for high transaction, low latency workloads. The i3 instances include the non-volatile Memory Express or NVMe SSD-based instant storage, which is optimized for low latency, very high random I/O performance, and high sequential read throughput, and delivers high ops at low cost. This also allows AstraZeneca to provide a performant and scalable search capability. Providing a centralized data hub of chemistry data on AWS has unlocked the data silos, creating a single source of truth for the scientist. Using scalable APIs, Amazon Athena and Amazon OpenSearch, the scientists and chemistry applications can access the required data depending on their requirements. This has created the foundations to build upon the drug discovery platform. But first, we need to understand at a high level the actual drug discovery process. The drug discovery process is generally arduous, costly, and success rates are low. Thus, the identification of a drug-target interaction has become a crucial step in early stages of drug discovery. Consequently, developing computational approaches capable of identifying potential molecules with a minimum error rate are increasingly being pursued. These computational approaches aim to narrow down the search space for novel drug-target interactions and how the drug functions and performs. Once a potential target has been identified and validated, we need to focus on lead identification. Drug discovery is often described using the metaphor of finding a needle in a haystack. In this case, the haystack comprises in the order of 10 to 60 to 10 to 100 synthetically feasible molecules. We're looking to find potential chemical compounds that have suitable characteristics to make acceptable drugs. In the industry, this is called a hit. There are various stages in this process. Firstly, Virtual screening is a computational technique used in drug discovery to perform searches across large libraries of small molecules in order to identify those structures which are most likely to bind to a drug target. With AI ideation, we're running a molecular de novo design through the use of deep neural networks. De novo design is the process of proposing new chemical structures that satisfy a desired molecular profile. With de novo design, it is possible for novel compounds to be suggested which are not in any database or library. Then we have ADME and tox predictions. The acronym ADME stands for absorption, distribution, metabolism, and excretion. And tox is short for toxicity. Toxicity is the degree a chemical compound could damage a human being. Scientists need to understand how a potential drug will perform within the human body. With lead optimization, this involves an iterative process to improve the characteristics of the identified potential compounds. Binding prediction or free energy perturbation calculations look at how a potential drug binds to a target protein. It's not just a case of whether it binds or not, but actually how well it binds to the target protein. Binding predictions using FEP+ show much better accuracy compared to traditional structure-based design using docking. And finally, we have synthesis prediction. Chemical synthesis, in simple terms, is using chemical reactions to get a product or several products. Scientists need to understand how to make the compound in the lab. Is it going to be safe and stable? Are there going to be any unforeseen reactions? With synthesis prediction, we're going to use machine learning models to predict whether chemical synthesis is possible. We're now going to go into each phase in more depth and look at how AstraZeneca have used AWS to accelerate each of them. Let's start with virtual screening. Computational scientists are often limited by available resources. These limited resources make it challenging to perform necessary scientific calculations, which have varying computing requirements and timescales. This can encompass very large-scale modeling calculations using chemical libraries containing billions of compounds. As such, scientists require access to an on-demand computing cluster, as well as better data sharing and collaboration capabilities. With this challenge in mind, AstraZeneca are using AWS partner OpenEye. The OpenEye Orion platform is a cloud-based molecular design platform for computer-aided drug discovery. Orion provides computational chemists with access to virtually unlimited compute resources on AWS. These include data visualization, collaboration, and workflow management tools to help them perform calculations more efficiently. At the core of Orion is the Orion Scheduler. The scheduler manages all the ongoing compute tasks. It uses Amazon EC2 instances for compute resources. When jobs are submitted on Orion, either via the UI or the API, the Orion Scheduler monitors computational capacity needed for each workload, which estimates the requirements by the rate of work completed. The scheduler then uses AWS auto-scaling to automatically recruit and return resources as needed, based on the recruitment requirements of the workflow and the scale of the calculation. Computations in Orion can take advantage of a wide variety of hardware available on AWS, including both CPUs and GPUs. Within the same calculation, users can switch between on-demand and spot instances, balancing cost savings against time to result. Users can define the hardware requirements across different parts of the same workload. The scheduler automatically places this work onto diverse hardware and automatically scales up resources when applicable. When the worker's instances are not needed, the scheduler turns them off. Orion Scheduler is aware of the cost of all the compute resources it controls. It automatically chooses the lowest cost hardware that satisfies the requirements of the calculation. This includes factoring spot versus on-demand, hardware density, and the scale of the workload. The scheduler allows a user to monitor the cost of the job in near real time while the job runs. The scheduler can set up notifications and cancellation thresholds to prevent accidental cost overruns. Amazon Aurora is used to manage user permissions and track collections of data shards. The shards of data are stored on Amazon S3 to be processed by the EC2 fleet. Amazon Elasticache is used to store metadata about running jobs and associated instant details as the job runs. The OpenEye Orion platform has provided AstraZeneca the ability to run high-throughput virtual screening using 3D similarity across billions of molecules, providing much better quality molecule hits, but also a more diverse set of hits. Scaling out horizontally across tens of thousands of EC2 instances provides scientists with insights much quicker than before and process much larger molecule libraries. Also, using AWS Spot instances has significantly reduced the cost to run these jobs, with savings of up to 90% compared to on-demand prices, depending on the EC2 instance type. Moving on to AI ideation. We're going to look at the platform which provides de novo design through deep reinforcement learning. Reinforcement learning is a machine learning training method used to reward desired behaviors and/or punish undesired ones. Like most large global enterprises, AstraZeneca has a number of applications which still run on premises. To continue to maximize this investment, the AI ideation platform runs on premises on a large high-performance compute cluster. It is key the platforms provide a consistent hybrid experience. To provide this consistent experience for the scientists, the front-end web application and control plane APIs run on AWS. Amazon EKS provides the scalable microservices platform as ideation jobs are pushed on premises. The scientists have the ability to plug and play components into the workflow and filter novel chemical compounds based on given criteria. This is a very iterative process. The end result is to be able to choose from thousands of novel compounds into a small subset of feasible ideas to take further on within the process. The AI ideation platform has provided the scientists with the ability to experiment with new molecular ideas using deep reinforcement learning at scale, providing potentially new molecular compounds to explore further. Delivering the front-end applications and APIs on AWS has provided common user experience for the data scientists across the entire suite of the drug discovery platforms. With ADME and tox prediction, scientists need to understand how a potential drug will perform in the human body. In this section, we look at how machine learning has been used and how it has been scaled to meet the demands of the scientists. AstraZeneca have developed the Predictive Insights platform, a centralized platform for hosting and serving machine learning models for inference. The design criteria for the platform is to provide scale, as the platform could serve hundreds of models with inference running against millions of molecules and used by many scientists. It's also key to reduce the time to load models, therefore accelerate the time to insight for the scientists. Previously on premises, this took time to achieve. The Predictive Insights platform models are provided from a number of sources, whether they are on premises, developed by HPC clusters or GPU workstations, or from the centralized MLOps platform within R&D called AI Bench, which is running on Amazon SageMaker, or externally from Melody, a groundbreaking collaboration to establish an ML platform to learn from multiple sets of proprietary data, or ML models built on the new NVIDIA One Cambridge platform. There are currently 80 models hosted, and the number is ever growing. As well as providing model deployment and hosting, the Predictive Insights platform provides model explainability and model drift. This is all fronted by a number of RESTful APIs which are integrated with various chemistry-based applications or called directly by the scientist. From an architecture viewpoint, I'm focusing on the view of the scientist. The models are containerized and are hosted as microservices with Amazon EKS, providing the horizontal scaling as the number of parallel predictions are requested from the scientists. The scientist calls the batch service API with batches of anywhere up to 100,000 molecules. Amazon Elasticache holds recent predictions. The batch service checks the cache results before sending the API on for inference against a specified model. Amazon Aurora Postgres is used to store state of the batch service. A separate Aurora Postgres database is used to hold and track predictions made against the different molecule batches. Similar to the creation of the molecular fingerprint we looked at earlier, as new molecules are added or updated in the data hub, a DMS task is running performing change data capture against the source Aurora Postgres database. These changes are sent to a target Kinesis data stream where a Lambda consumes the batch service API. Some base predictions are made for each new molecule, which can be accessed straight away. With over 80 models hosted on the Predictive Insights platform, AstraZeneca have a great insight and accuracy into potential ADME tox predictions from a molecule compound. But over the past couple of months, over 80 million predictions are made on the platform, with that number only increasing month on month. Amazon EKS has provided the scalable backend, allowing the different model APIs to scale horizontally as required. Additionally, the model deployment time is reduced to less than a day from what was significantly longer time on premises, with the future vision for model deployment to become self-service. Binding prediction or free energy perturbation calculations will look at how a potential drug binds to a target protein. It's not just a case of whether it binds or not, but how well it binds. Let's take a look at some of the historical challenges running FEP calculations. Traditional structure-based design using docking is a poor method of ranking compound affinities. Binding affinity predictions for small molecules using drug discovery and FEP shows much better accuracy. However, running FEP calculation requires a large amount of high-performance compute backed with GPUs. This becomes a costly CapEx outlay for many organizations, which significantly limits the use and reduces the scientific impact. AstraZeneca used an AWS partner solution from Schrödinger to run the FEP calculations. Underpinning the platform is the Amazon EC2 P3 instances. Depending on the instance size, either 1, 4, or 8 NVIDIA Tesla V100 GPUs are inside to accelerate the binding calculations. As you're probably aware, we released the P4D instances, which is the 8 NVIDIA A100 Tensor Core GPUs on board. We're currently working with both Schrödinger and AstraZeneca to review the performance of these instances. Depending on the required accuracy of the binding predictions, each prediction can take between 2 to 3 hours for low accuracy or up to 24 hours for high levels of accuracy. AstraZeneca running the FEP calculations using the P3 8x large instances to scale horizontally, processing 24/7, which today has delivered around 300,000 FEP calculations per year. Using the Schrödinger FEP Plus platform has significantly increased the accuracy of the molecule binding predictions, which in turn reduces the overall lead optimization time and also cost down. The FEP platform provides an active learning capability where it trains a machine learning model based on the predicted binding affinity. This allows for predictions on new molecules to be generated much more rapidly as it filters compounds before the FEP run. The P3 EC2 instances have provided the required horizontal scale and performance to meet the demands of the scientists, accelerating the insight back to them with improved binding predictions. Finally, we're going to take a look at synthesis prediction. Chemical synthesis, in simple terms, is using chemical reactions to get a product or several products. With synthesis prediction, we're going to use machine learning models to predict whether a chemical synthesis is possible. This allows the scientists to make the compounds faster and more efficiently. To use machine learning models to predict synthesis, historical reaction data is used to build and train the models. This data may come from third-party providers such as Reaxys or Pistachio, or internally captured historical experiments using electronic lab notebooks. These provide a rich source of millions of reactions to build the machine learning models. Currently, the majority of the models are built and trained on premises and stored in a model repository in S3. The machine learning models are containerized and hosted on Amazon EKS. A layer of RESTful API microservices provide the front-end access to the AI's internal application. Currently, an in-memory Redis cluster is deployed directly on Amazon EKS. The Redis cache is checked for synthesis results before inference is run against the model. AstraZeneca are currently investigating the use of Amazon Elasticache for Redis as an alternative to hosting on EKS. Amazon Aurora PostgreSQL and Amazon DocumentDB hold application state data, user preferences, and additional synthesis data. AstraZeneca are using Chemtrack's application from Elixir to track the design, make, test, and analyze process, allowing them to track synthetic targets across multiple projects and partners. When a molecule is entered into Chemtracks, its synthetic route is then automatically predicted by AISynth. A message is sent from Chemtracks to Amazon SQS. A Lambda function is then used to process the incoming message. The Lambda function calls the AISynth APIs to predict synthesis routes. For the scientists, this results in just a one click to view and explore, making a great user experience. Access to large reaction databases, both internal and external, has allowed AstraZeneca to build machine learning models to help predict synthesis. The end result is it saves the scientists valuable time in the laboratory by predicting the best way to make a molecule in the shortest amount of time. Now, let's do some chemistry. Time to enter the lab and experiment. In this quick overview, we've taken a target protein, used vast quantities of data, molecules, compound libraries, AI and ML, and high-performance compute. We've narrowed down to a number of potential candidate molecules which could work, saving a significant amount of time, is economically beneficial, and improving the overall accuracy of the results. Now, I'm going to hand back to Anna to look at how these outcomes have had for AstraZeneca, the lessons learned, and what's next.
Thank you very much, Chris. So, what were the outcomes? What were the lessons learned? And what's next? So let's start with the outcomes. So we got significant reduction in drug discovery time. And we got over 200 hosted data and AI endpoints. We had model deployment down to less than 24 hours. Great outcomes. So what did we learn that may be relevant for all teams and all challenges around this case? We worked very closely with the chemists. AWS, our IT teams, and the chemists all worked as one team and had one shared top-line objective. And we still have that top-line shared objective. When we talked about investments and the vision, we were all using the same metrics of success, and we are now measuring the implementation with the same metrics. On the tech side, we needed product-focused teams, agile delivery, and they could deliver on challenges very quickly. And those teams worked very, very closely with the chemists. So where will we focus next? We are working closer than ever with our scientists to find new opportunities to unleash the power of tech into the research. And we are scaling our current successes to more users and new areas. And the future is incredibly exciting. Thank you.
Thank you, Anna. In summary, we have seen how AstraZeneca have accelerated their drug discovery process on AWS. They've made the conscious organizational decision to create product-focused teams delivering the drug discovery platform using DevOps culture, practice, and tooling. They've used modern microservices-based architectures, allowing the platform to scale as required, alongside using managed services to reduce the overall cost of ownership. AstraZeneca removed the data silos and combined the use of ML to accelerate and improve the accuracy of discovering new molecules. And finally, using the scale and reliability of AWS cloud services to find insights they've not been able to achieve previously on premises. I'd like to thank Anna for joining me on stage today and telling us all about the exciting journey AstraZeneca have been on. Most importantly, thank you for joining us at this session. I hope you've enjoyed it. Thank you. Goodbye.